Good morning, ladies and gentlemen. Today we talk about distributions. When do we talk about distributions? I want to give you both a philosophical approach to what it is, because many people are confused, and also see it from different angles, particularly in the field of Fourier calculus and in statistics. So let's start with statistics because that's the easy part. So in statistic, a distribution of probability is, for example, in the space where the fact can happen. It could be me throwing an arrow and the distance between the center and where the arrow arrives. That's a monodimensional distribution. And if it should be here, probably the distribution will be something like this. Or it could be if I roll a die with 20 faces, I have 1/20th, or let's say 1/6 for a normal die, 1/6 to be here, 1/6 to be here, and it's like 6 dots, right? So this is like a distributed distribution, and this is like a punctual distribution. So it's like discrete and continuum, because I think distributed is a very silly word in this context. Okay, so in probability, the sum of all the possibilities is 1. Is 100 by the definition, is 100%. Tomorrow it might rain 75%, or it might not rain 25%. But the sum is 100%. If the sum was 150%, maybe you should change your YouTube channel and listen to someone else, because probably what they're saying is bogus, right? So the sum is 1, and this is an important property. So every time we talk about distribution, usually we assume the area of the integral of this blurb is 1. 1 as 100%, okay? 1 is a magic number, okay? It's the second most important number after 42, right? So this is your distribution. So that settles statistics. Now, in Fourier, distributions allow you to define pragmatically things that cannot be defined in the normal world. It's a bit like complex numbers. We invented them because we need them to describe things that cannot be described without them, but they're kind of untouchable. Like it's something you cannot really touch with your hands. Like you can touch the number 3. You can even touch pi, but you cannot touch a delta of Dirac. So let's start with the delta of Dirac, which is the most important distribution, and she's the queen of the Fourier transforms, okay? So a distribution can be described as a succession of functions. So think that you have a function defined from R to R, from real to real, and this is easy peasy. We already discussed that. If you don't know what a function is, change video, because this will be too complicated. So, but if you know what a function is, let's stretch the definition. Let's define f1, f2, and fn as successions of functions. And I don't care about f1 and f2 and fn, let's be honest. I care about the infinite, like the tendency. How does it behave at infinitum? And I can also give you an example, but before I give you an example, I want you to see the stratification over, I want to see how complicated this is. So imagine that this is f1, and this is f2, and this is f10. Okay? You could say, oh, I see where you're going, and maybe you're going to the point where at infinitum you have like a Gauss thing that is very, very shallow, and the dot goes here. Something like that. This is a silly example, but to say, would I care about what is the limit for n which goes towards infinitum of f with n of x, okay, or of t if you want. So these are many, many functions. What is the resulting function when n goes to infinity? Now the interesting part of that is that often there is not such a function. It's impossible. You can have, because a function is like an array of numbers, and I would say, what is the limit of the array of numbers? You could say, well, that's a very stupid question because you have many numbers. Ask me the limit in -5. That I can tell you, because the limit of the f in -5, it's a lot of function, it's a lot of points, and all those points maybe converge to 0. That is an easy answer. But where does it converge? The whole function, the whole blah blah blah, that is much more difficult. And in general, there's no answer to it. In general means if you're unlucky, there's no answer. If you're lucky, there is. Oh my God, I can give you hundreds of examples where there is. But I can also give you a few examples where there isn't, right? So distribution is the concept of I give you a number of functions, I will call it fn, and I give you a limit, but like Barney's thesis, I will say, wait for it. Don't integrate. I know you're tempted to do the limit, but don't do it just yet. Do it at the end of anything. So I could say, I want to inject this inside an integral and integrate this, for example, doing a convolution between this and something else. I say, oh, that's a great use case. Wait for it. If it was a magic card, delta d Dirac would be when this function comes into play, sacrifice it unless you're inside an integral. Because that's what it is. Now you say, oh, I'm confused. Of course you are. Let's get a real case scenario, okay? Let's take the delta of Dirac, the most important of them all, the simplest and more complicated at the same time of them all. Did I get you curious? I hope so. So, the delta d Dirac can be described, can be created in many, many ways. The simplest, in my opinion, to teach is as a rectangle that is defined between minus epsilon and plus epsilon. So it's like a rectangle of base 2 epsilon and of height 1 divided by 2 epsilon. So as you can see, the area of this rectangle is 1. So the probability folks are happy. The Fourier folks don't give a shit, but the probability folks are happy. Let's make it's free. Let's do it, right? So I could say, since I want, so this f is defined as out of this is 0. Inside this, so if for t in minus epsilon epsilon is defined as 1 divided by 2 epsilon. Since epsilon goes to 0, we might want to use n equals 1, we want to define it with n, okay? So let's revert epsilon, so it's defined as 0 or n divided by 2 between minus 1 on n and plus 1 on n, okay? Else, and here elsewhere. You like elsewhere? It's a very mathematical concept. Okay, but anyway, you know what I mean. So what does this mean? This means that for, if you're lazy, you start here. This is a rectangle of area 1. And then you get narrower and narrower and narrower, and then you get bigger and bigger and bigger, like your function is having an erection. Okay, I'm sorry to say that. But what is the limit at infinitum of this stupid, super amazing function? Well, if you think about it, if you really cannot avoid doing the limit of this, well, it's very simple. This function is 0 everywhere, except in 0. So in 0 it's not defined. The punctual limit in 0, like punctually, if you have a whole afternoon and say, let's do the limit for n which tends of infinitum of f in, I don't know, in 1. Well, in 1, after a certain n, it's 0. In 0.1, 0. 42, 0. My God, it's always 0. But what about in 0? Oh, this gets interesting. So, whatever n you get, you always get into this point, right? You don't get into this point. So it's n divided by, it's like n divided by 2 in 0. And n divided by 2 for n which tends to infinitum is in plus infinitum. You know, infinitum, if you divide it by 2, is always a plus infinitum. So it's always a positive infinitum. It's an incredibly high number. So if you want to really graph this shit, because it's totally shit, it's totally unusable, it's basically 0 everywhere and plus infinitum in which you cannot graph. That's why I say shit. Like Cartesian graphing of this function is totally pointless because it doesn't exist. This is a function which is basically 0 everywhere and not defined in 0 or defined as infinitum. It would be better if it was defined as 42, but it's useless anyway. You cannot do anything with this function. It's a stupid function. Why is it a stupid function? Because you insisted on doing the limit. So I say, can you please hold back and don't do the limit and wait for it. Follow Barney's thesis. Wait for it. Okay? Now, we have this function and we wait to do the limit. Why is it useful? Because now you can do something like, I don't know, the convolution or the Fourier transform. Let's try to integrate this delta of Dirac multiplied by another generic function. So the integral of between minus infinitum and plus infinitum of a generic function f and delta. Oh, now we are thinking. So delta will give you a little rectangle that selects f only in 0, and elsewhere it doesn't give you anything. It's not super easy to prove, but you can assume, and probably you're already thinking, that this selects the function in 0. This is why in telecommunication this is really important, because delta is basically a selector, an integral selector. So when you do convolution of two functions, the convolution of two functions f and g is defined as the integral of over r of f of tau g of t minus tau in the tau, and this gives you a function of t. So you're basically taking the two functions, give them an offset, and calculating the area of that depending on the offset, right? Where the offset is 0 is one above the other, right? And the delta of Dirac gives you that information. So why delta is not a function, but acts like a function when you're inside. Oh, sorry. Acts like a function when inside an integral, for example. Now, the mother of this queen is the function of Heaviside. If you do integrate this, again, you cannot because it's a function, but if you do it inside an integral and you do some calculation, you find out that the integral of this is this. What is the derivative of the delta? Well, when you do a derivative, I think the best way to do a derivative, if you're a cyclist, is thinking that you're cycling over that function, right? So think of the delta, this time think of it like a nuance as like a hill, right? The area is 1. What is the derivative? So it's how tough it's for you to cycle, right? Positive, very tough. Negative, you don't cycle at all. So here, from it's always 0, and then you start going up, but it's very easy, it's very easy, it's very easy. Here, this is the toughest moment of the day. This is where you're really cycling, and it's really tough. But now this is a flex, and now it gets better. So the dependency of it's lower, and it gets to 0 here, because you know the derivative of a maximum or a minimum is always 0. So here it's 0. Here for symmetry is minus this, and then it gets to 0. So what you get is something like this. I finished the color. Let's do it in green. This is what I call a hard bit, right? So the derivative of the delta is actually a hard bit. I think you can prove integrating by parts that this is minus delta divided by t. So the derivative of the delta is another delta, but divided by t multiplied by a constant. This is really interesting. And the integral of this, well, the area from minus infinity to a generic point, well, this is quite obvious. So 0, 0, 0, 0, 0, 0. Here the area is 1, so it will be 1, 1, 1, 1, 1, 1. And then you get all the degree in between. So it's something like this. This looks like an arcotangent, right? In fact, I like to define, this is the function of Heaviside. So at the infinitum, this is the integral of the delta. This is the derivative of the delta. I also put the Poissonian, the Poisson function, because it's very good at modeling in engineering the medium duration between the breakage of things. So if you have a new router or a new computer, how much time passes between before you need to buy a new one? That is exponential of minus negative lambda t, with lambda is the parameter of probability of breakage, right? Is basically the inertia radius of your breakage, multiplied by lambda, so the integral gets 1, so the statisticians are happy, right? This is also quite important in distributions, but not from this mathematical aspect. So again, distributions, wrapping up, are in general are defined usually as a limit of a function, and that punctually might not have a sense. So you keep the limit in your pocket. It's like you're playing poker. You keep it there and say, I see your cards. Ah, you only have a trace. Dang, I win. But you cannot do the limit before you do something with the function. Otherwise, the function will crumble to pieces. Okay, that's why it's like an extension of a function. It's like a virtual function, if you know C++. It's important in statistics because it has a very easy explanation because it describes what probability can assume at the variation of the variable for which the probability is being studied. And in Fourier analysis, I want to show you another important thing of the Fourier analysis. You might know that in Fourier analysis you have an impulse like something like this. Any periodic function in the domain of times has a transform in the domains of frequency, let's say omega, okay, that gives you how many, what is the energy of that function at the various harmonica, like, I don't know, like 100 hertz, 200 hertz, 300 hertz, provided that the frequency, the period of this is 2 pi for this f, right? So f, 2f, 3f, 4f, etc. So it will have an energy here, an energy here, an energy here, an energy here, and so on. This is like a generic Fourier transform. The beauty is that if you take the function 1, so 1, so it's always 1, again, one of the most boring functions in the world, the Fourier transform of this is quite obviously, drum roll, is a delta of Dirac. Why? But think about it, it could be expressed in the continuum, it's expressed like this. In the discrete, it's expressed like dot, 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 and a big dot with infinite energy, but in physics, infinite doesn't exist, so this would be a finite number, right? Also, for the theorem of Shannon, you have like a maximum frequency where you sample, so this is always a physically delimited number because this is the energy of your signal, right? So also the time is not infinite, you know, for a number of reasons. But the beauty of this is that the transform of 1 is delta, and the transform of delta is 1, because remember the Fourier transform is involutive, so applying it 2 times gives you back the function. How beautiful that is, right? So the physical y delta of Dirac is so important is because this is the auto-vector of the Fourier transform, okay? And is the auto-vector of convolution. So is the neutral element of multiplication of a convolution. So when you convolve f with a delta, you still have f. And this is given because the Fourier transform of f is big F. This is, I don't know, but this, the Fourier transform of delta, if you remember, is the boring one. Boring one is not the number 1, it's the function 1, right? It's always 1, and f by 1 is f. So I proved you very, very simply, well, if you assume the theorem of Bonelli, Fibuli, some Italian dude, the Fourier transform of the convolution is the multiplication of the, so what you convolve in time, you multiply over frequency, and vice versa. What you convolve in frequency, you multiply over time, right? Well, I don't know, I hope it was useful. I don't know if it was clear. I hope I gave you some philosophical and pragmatical definition of why distributions are useful. Thanks for listening, and please, any criticism, write it down so I learn, and maybe I cast it again if I forgot anything. Thank you very much. Bye.